Welcome to The Explainer. Today, we're going to step right inside the heart of a flour mill to really understand the science and, the art behind getting that perfect grind. It's a process of incredible precision where the tiniest adjustments can make a huge difference. Okay, so let's get right into it. What you're looking at here is a roller mill. And its whole job, its entire reason for being, is to take a wheat grain and just crack it open. But how it does that? Well, that's a fantastic mix of some pretty powerful engineering and some incredibly delicate control. And right at the absolute center of this whole process are the grinding rolls. This is it. This is where all the magic happens. It's where that transformation from grain to flour really begins. So every single grain has to pass through this microscopic space between the rollers. It's called the nip. And in that tiny gap, the grain gets hit with this immense pressure and shearing force. It's being crushed and torn apart at the same time. And how that happens is anything but random. So that brings us to the big question, right? What levers does the miller actually have to pull? How do they control this whole thing to get the exact result they're looking for? Well, it turns out the final product is all down to a few key factors that every great miller has to master. And you can really think about these factors in two main buckets. First, you've got the physical design of the machine itself, the stuff that's built in. And second, you've got the operational settings, the dials the miller is constantly tweaking during the process. So let's start with the foundation. Before a miller even thinks about flipping a switch or turning a dial, the actual physical design of the rollers totally sets the stage for what's even possible. Now, if you could get a close look at these rollers, you'd see their surface isn't smooth at all. It's covered in these sharp grooves, or what millers call teeth. And the specific design of these teeth, it's absolutely crucial to the entire operation. And when we're talking about the design, it really boils down to two things. First, how many teeth are packed into a certain space? That's their density. And second, the angle that those teeth are cut into the roller. And this is where it gets really clever. The strategy actually changes with each stage of milling. You see in the table, for that first break, you're only using 4 to 6 teeth per centimeter. The goal there is just to give the grain a good, coarse crack open. But as you move along, the density of the teeth goes up, which allows for a much finer, more precise scraping and cleaning action in those final breaks. Okay, so the next piece of the puzzle is the angle of those teeth. It's called the tooth inclination. See, the grooves aren't cut straight, they have a spiral to them. And that angle, which we talk about as a percentage, is so important because it changes how energy is transferred to the grain. It's what determines the balance between a sharp cutting action and a more gentle scraping one. And yep, you guessed it, just like with the density, this angle changes as we go. The angle of the teeth gets steeper in the later stages. You use a shallower angle for that first big cut, and then a steeper one for the final, really delicate job of scraping the last bits of endosperm off the bran. All right, so that's the fixed design. Now let's talk about the stuff the miller is playing with in real time, the speed of the rollers and that all-important gap between them. Now here's the secret sauce. The two rollers in a pair, they don't spin at the same speed. One is always turning faster than the other. This speed differential is what creates a powerful shearing force that tears the grain open instead of just crushing it flat. It's a huge deal. And that's really the bottom line, isn't it? By adjusting how much faster one roller is than the other, a miller can literally dial the intensity of that shearing force up or down. A bigger speed difference means a much more aggressive tearing action on the grain. So let's put it all together. What happens when you combine the tooth design with these operational settings? Well, it all comes down to creating two very distinct types of grinding actions. So depending on the tooth angle and the roller speed, you're either going for a powerful shearing action. Think of it like grating a carrot, which is awesome for cracking the grain open at the start, or you're creating a scraping action, which is much more like peeling that carrot, and that's perfect for delicately removing the last bits of valuable endosperm from the bran. And this right here is a fantastic way to see that concept in action. It shows how the teeth can meet up in different ways. Are you setting them up sharp edge to sharp edge for a nice clean cut? Or are you going dull to dull for more of a crushing effect? The miller can fine-tune the grind at a literally microscopic level just by changing this orientation. You see, when you start to get all this, you realize that milling isn't just some simple mechanical process. It's a true craft. It's this amazing blend of deep scientific knowledge and that hands-on artistic intuition. So, to wrap it all up, the miller's craft really comes down to mastering these key levers. You've got the fixed design of the roller's teeth, that's your potential. Then you've got the real-time operation, especially the roller speed, which is how you unleash that potential. And when you combine those two, you get the final result, whether that's coarse semolina or super fine flour. And like the source material says, it's always this tricky balancing act. The miller is constantly juggling the need to get the highest possible extraction rate with the demands for top product quality, all while keeping the entire mill running at peak capacity. It's a really complex problem they're solving, minute by minute. By mastering these principles, tooth design, inclination, roller speed, a miller isn't just operating a machine. No, they're more like a conductor, conducting a finely tuned process. They are the artists and scientists who make sure every single grain of wheat gives up its absolute best to get that perfect, efficient result.